I always tell people, you come to this institute, we only talk mathematics. But that's never true, obviously. The whole book, everything I say is, in the background is how you can teach better. Right? So in some sense, I'm lying. And in fact, I will explicitly break it now, break this thread of only content. This is such a complicated algorithm that, on the one hand, I don't think you have, well, this one, for example, this one. I don't think you're going to do this in the 6th grade classroom. Can you imagine? Even this?
Yeah.
You do?
This particular one? The single digit?
No, this one. This one.
Yeah, fifth grade. 4th grade.
What?
Single digit division.
No. All I'm talking about is explaining.
Oh, you mean the proof? Oh, no.
Now, yeah, so yesterday I did the same thing, and people say, oh, what do you mean? We're at the stage where I assume you know this, when I'm not even talking about this. If I say you want to do this, of course, I'm a talk, but still, I thought you understand. I'm not interested in this. I'm interested in what we've been doing with this, right? The explanation. I don't think you can explain something this complicated in a 6th grade classroom. However, I think it's perfectly feasible for you to explain something like the one I gave you yesterday. That's doable. It was only about 2 steps. And that's actually good enough. Because what do you want to achieve when you teach? You want to send out a signal that, well, you may not understand the whole thing, but at least you get a glimmer of an idea that even if you think it looks mysterious, but there is solid reasoning behind it. Trust me. You can achieve that, 90% of your battle is basically won. So if you do this clearly, make them see, yes, at least in this simple case, you see the reasoning. Then they can sort of talk themselves into thinking, well, okay, I may not understand something complicated like this, but it must be more of the same, so when I grow up, I'm going to learn it. Sort of like that. And so I would suggest that do at least something of this nature, or something 32 divided by 2 or something, whatever. Just do something simple enough. Give them the belief that what you do makes perfect sense. Sometimes you do things not because you want to achieve complete understanding. Rather, you do something to make them hold out the hope that they may not understand it now, but they will at some point. And that's almost good enough. Because mathematics has to be something that's understandable. If they still hold on to the belief that it's understandable, that's switching. All right, now, so in the same vein, I want to talk about this algorithm that, now the real explanation, as I said, that this algorithm is everything we did. But you can cheat. You can at least make students feel that, even though something this complicated, in fact, you can tell them what it's all about. And not quite an official explanation, but it's almost as good. You do it in some sense you're cheating, but it's a cheating for a good cause. It's written in the book, so I don't think you should bother writing anything down. Which is, I use money to give us half explanation. Now, we know this is 146. Oh, yeah, it is 146. Now, why is this so good? Because, as we said, what is the meaning of division with remainder? It is what? Once you know what the divisor is, I'm asking how many copies of the divisor, maximum number of copies I can fit into 879. Remember that, right?
Yeah.
On the number line, you keep going up and up until you come to the last one, and the next one exceeds it, then you say we're stopping. Right? That's the real meaning of division with remainder. But I can cheat now. I'll write it as this one. Now, it's definitely cheating, because why? Until you have done the calculation, you don't know what that is, right? So it's hard to talk about. But this is that's why I'm cheating. I'm saying, imagine you know 146, you know it's 146, so you can think of it concretely. So what does it say now? Well, that do it this way. First, it's equal because commutative, right? But this is the difference between measurement interpretation of division and partitive, right? That division with remainder is brute force measurement interpretation. You keep chopping off copies of 6 and 6 and 6 and 6 until you exhaust it. This is what? Even if you don't know what it is, right? See, this is very bad because you have no idea what is in it, right? Still allow yourself to think like that. So what you're saying is that 0 to 879. You're saying, well, there is a possibility of locating something here so that when you divide it into 6 equal portions, what's left over here is not going to be bigger than 6. And then the size of one part is what we call the quotient. Does that make sense to you? Right? Now, I hope I'm making sense to you, but you also know, I hope you also know that I am cheating my lesson. Because I'm not telling you where to start in the first place. Right? Nevertheless, there's some advantage because if you allow yourself to believe in that, then you say division with remainder is an issue of distributing 879 objects into 6 piles so that they come out with the same amount with a little bit left over. What's left over, of course, not matter. Let's just say there's some left over, you cannot do it anymore, right? Does that make sense? Okay. Let me repeat. You reinterpret this as saying, I have 6 piles, this is a big divisor, and I want to distribute 879 objects, whatever they are, into 6 piles, so that each pile comes up to be exactly the same amount as any other. And you allow a little bit of leftover. Is that good? All right, now, that's how I'm going to proceed. Okay, so what I think of is what? This is 8 $100 bills, right? 7 $10 bills, and then $9 bills. You're going to distribute the loot among 6 criminals, right? Each one gets equal share. You have 8 $100 bills. That's easy to deal with. Put one in each, right?
Yeah, 6 of them.
There goes $600. You have $200 bills left, and you don't want to cause any fights, so you're not going to use that to put in 2 of them. Rather, you say you exchange. In exchange, there are 20 $10 bills. 20 $10 bills, right? But you already had 7 $10 bills, right? Now, in your hands, there are 27 $10 bills. Oh, look, that's exactly what this is. You can distribute 27 into 6 parts, 4 each, 4, 6, 27, right? The 4, you put in 4. You put each part, you put in 4 $10 bills. Now you'll use up $240. You have 3 $10 bills left. And again, you don't risk causing any fight. No more distribution. You exchange the 3 $10 bills to what? $31 bills. $31 bills. Right? You do that. But you already had 9. So in your hands now, you will have 39 $1 bills. Distribute again. Each, yeah, 6. Yeah. There go $36. So you have 3 $1 bills left. And now you say, well, clearly you cannot do any better at this point. Unless you break into dimes, you're stuck. So just let it go. Give it to the bellboy. So now you have each part has how much money? 146. That's